Good day, grade 11s. I'm going to explain the table on page 29 in your physics textbook. The first situation is one where the object is resting on a slope or an incline. If the incline has an angle of theta and the object has a mass m, then the weight of that object will act down perpendicular to the horizontal plane. So that would be the weight of the object. The weight of the object pushes the object down onto the plane with a force that is equal to the perpendicular component of the weight to the plane. So that is called Fg perpendicular. The weight of the plane of the object also causes the object to want to slide down the inclined plane. Now that component of the weight that wants the object to slide down the plane is called the Fg parallel to the plane. Now because the object is resting on the inclined plane, there is also a normal force that acts perpendicular to the plane up on the object. So this is your normal force. If the object is resting on the plane, it means that there is something keeping it from moving. So that is the frictional force. And if the object is stationary, it will be the static friction acting on the object. And if that object is that incline is such that the object just wants to start sliding, so it would be the maximum static friction acting on the object. Let's analyze the situation. There are three forces acting on the object: the weight, Fg, the friction, Fs max, in this case, doesn't have to be max, and the normal force that makes an angle of 90 degrees to the incline. Now, the component that wants to pull the object down the incline is Fg parallel, which we can calculate. That angle there is the same as the angle of the incline. So that angle there is theta. It is Fg sine theta. The component of the weight that is perpendicular to the plane is Fg cos theta. Okay, now the normal force Fn would be equal to the perpendicular component of the weight Fg cos theta, whereas the component of the gravitational force wanting to pull the object down the incline, that is Fg sine theta. But if the object is stationary, this Fg sine theta would be equal in size to Fs max. Because the friction prevents it from sliding down. So there is no motion. So these forces are, all of them are balanced. So Fs max is also, per definition, the ratio, the mu s times Fn. So mu s, because mu s, the coefficient of static friction, is the ratio between Fs max and the normal force. Fs max is mu s times Fn, and we know that Fn is Fg cos theta, and that gives us Fs max. In number 2, the object is sliding down the slope. So the forces acting on the object will still be gravity, Fg, the normal force, Fn. Its movement is down, so there will be an upward friction, Fs. But no, it's moving, so this would be the kinetic friction, Fk. The component of the weight that causes the motion down, that is Fg parallel, and we know that Fg parallel is Fg sine theta. The normal force would be equal to the component of the weight, so if N would be equal to, in size, to the component of the weight that is perpendicular, so that is Fg cos theta. Now, if you have no acceleration, the net force, which is Ma, would be 0. Now net force, F net, would be equal to the Fg parallel component minus the Fk component. If your F net is 0, then Fk would be equal to the Fg parallel, which is Fg sine theta. But Fk is also in a relationship to Fn, so the ratio between the Fk and the Fn would be the coefficient of kinetic friction, which is Fk over Fn. So Fk can also be calculated by taking mu k and multiplying it by the normal force, which would be Fk, the normal force is the perpendicular component of the weight, Fg cos theta. In the third situation, the object is pulled up the slope. This changes a few things. You've still got the weight acting on the object. You've got the normal force acting on the object. You've got a pulling force, F pull on the object. Now, you've got the frictional force downwards. If it's moving, then it would be Fk. The situation is the following. If it's moving, then it's possibly moving at a constant velocity, but it's not to say it would be moving at a constant velocity, so there will be a net force acting on the object, which is the mass times acceleration, which could be a zero acceleration. Fact is that the net force now, the MA, equals the F pull minus the Fk, and the parallel component of the weight is also there, Fg parallel. So it's minus Fg parallel. So in reality, your mass times your acceleration is F pull or F applied minus Fk. Now this Fk would still be equal to mu k times Fn, which is mu k times Fg cos theta. So I'm going to write it as that. Mu k Fg cos theta. And F parallel is Fg sine theta. Right, the last one, the object is pulled down the slope, so the motion would be down the slope as well. So you've got Fg acting, sorry for my squiggly line there, should be a straight line. Fg parallel, Fg, the normal force will still be acting. Now it's being pulled down the slope, F pull. The friction would be up the slope, it's a kinetic friction, and the component of the weight that is parallel to the slope will be in the same direction as the pulling force. So the following stays the same. Fk would be mu k times Fg cos theta, and the component of the weight that is parallel to the slope remains Fg sine theta. We don't know whether this thing is accelerating or moving at a constant velocity, but the F net remains ma, but it's also the F pull minus plus the Fg parallel minus Fk, because it's in opposite direction. So F pull plus the Fg parallel, which is Fg sine theta, minus the mu k Fg cos theta. I hope this helps you, makes the table clear. Please let me know if it doesn't.